So we've already seen that most bodies contain two types of energy. Okay, so as an example, a body floating above ground will represent the body by this structure here, just randomly that structure there. I'll put a bit of rotation on it as well. Okay, so we have you have a center of gravity. Okay, where all the weight acts through the center of gravity of an object. Okay, so it's like the balance point where all the weight acts. Now, its position above the ground, you can call that a high H. So it has two types of energy, mgh, and which is potential energy, and a half mv squared, which is kinetic energy if it's moving downwards. Okay, so if it's on its way down. I can't do that like that. So if it's on its way down. Now, so that's grand. What it says is that like the conservation of energy states that it has to be constant. Like potential energy gets converted into kinetic as you lose height, right? So the sum of all the energies as a whole is constant. Okay, so your energy system as a whole is constant. But if there's a rigid body and it's rotating, okay, so in some cases you can have a body that's actually just rotating around an axis, still moving, but sometimes the height doesn't have to change, or it can be moving and rotating at the same time. So there's got to be a measure for turning motion. Okay, so this is what we refer to as we need to find out the angular velocity. Remember we did it in circular motion, where omega is the angular velocity. Okay, so that's we're talking about omega here being the how much angle you cover per second, or radians per second, about some axis. How can we measure its potential and kinetic energy? Okay, so what we have here is firstly potential energy is mgh, where m is the mass of the body, h is the height of the center of gravity above some standard position. As in my last diagram, center of gravity, or COG, was there, and it's above a standard position on the ground. Now, secondly, the kinetic energy of the rotating body is the sum of kinetic energy of each small piece, delta m, in the body. So if we're going back to this body here, I'll do the same one again, or roughly the same one, and so imagine its center of gravity is here. Okay, there's tons of little pieces that are rotating, and each one has a different. Do you remember about remember your actual velocity? Okay, your actual velocity depends on the radius you're away from the center of the rotation. Remember, phi equals r omega, or omega equals phi over r. The problem here is that if this is your center of rotation, each individual little piece, so you could say the blue piece and maybe the purple piece, they rotate with different velocities, don't they? They might have the same omega value because they're part of the same body, but they actually have different velocities. Can anybody tell me why the blue dot would have a different velocity to the purple dot as it's rotating? Sorry? Not necessarily the law of the lever, but it's the right principle. Is that it's closer to the center of rotation. Okay, so basically, if you look at this diagram here, you can see that the blue dot is further away than the purple dot. So when the full body rotates around the red dot, the red dot is like an axis of rotation. It's just rotating around the red dot. So you can rotate this way. The full body's rotating. But in that time, what you'll find is that the blue dot will cover this much distance in a full cycle, while the purple dot will only cover that much distance in a full cycle. Hence, the blue dot has a superior velocity to the purple dot. Alright? And we have to do this for every single piece of the puzzle, where it's up here, down here, up here, down here. We have to find some way of accounting for every single little piece. Okay? So if you imagine that each of those pieces represents delta m, a small piece of the mass of the overall body, a minuscule, tiny little piece of mass of the full lamina. Lamina is just like a 2D object, like a rectangle or any 2D area. Okay. So what happens is the full body is rotating, and what we have to do is we have to use this E sign. Everybody familiar with the E sign here? It means sum of. It means we're adding the kinetic energy. That's the kinetic energy formula. We're adding the kinetic energy formula of every single little piece individually. Okay? So that's what this E stands for. Now what we do next is we change velocity into R omega, and now we have kinetic energy. It's the sum of the kinetic energies of every little piece, but we're using angular velocity. Okay? Then you scroll down a bit more, and what we do is, since V equals R omega R, where R is the radius of each piece, circular motion about the axis of rotation. Alright, so the kinetic energy can now become this. Now see that half omega squared, yeah? That's a constant, because your angular velocity of your system would have been constant. So if I was rotating the full system, it's trying to rotate around the red axis. It's not quite centered, but you get the gist that everything's covering a different velocity. Okay, so what we have here is kinetic energy is a half omega squared, the sum of all the individual masses, is what delta m means, and r squared means the distance they're away squared. Okay, now the principle of conservation of energy for a rotating body reads: your potential plus your kinetic energy equals your height above ground plus your rotational energy, where all the energy gets put into rotation. Okay, is a constant. The definition inertia, okay, see the way it's a half I omega squared. A half I omega squared refers to the rotational kinetic energy. Okay, next thing we have to figure out is what on God's green earth does I mean. Okay, so if you look at the last slide, we figured out it was a half omega squared. This part here is the I value. Okay, so this part here refers to the I value. Okay, so we have next is I, oh dear, I therefore equals the sum of all the masses individually multiplied by that individual masses distance away from the center of rotation squared, or radius squared. Okay, shows that the moment of inertia of a body about a fixed axis depends not only on the mass of the body, but also on how that mass is distributed. Let me explain that to you now. Okay, so remember we said that we had to add up each individual piece. Yeah, if you look at where's my diagram? If you look at these two bodies, okay, and both bodies are of same mass, is that okay? Which one do you think is more difficult to turn? Huh? The one on the right. And I'll explain why. Its mass, a lot of its mass is located at a much greater distance away from the center of rotation, while this one's mass is all located within that much distance of the center of rotation, the center of gravity. So that's the rotational axis there. We're rotating around this way, or clockwise or anti-clockwise, using the plane of the page. Okay, but what you'll notice is that this line here, that one's not too bad. It's actually long, but this one here, you can see it's considerably further away. Okay, so it's basically, as Adam might be mentioning, a bit like the law of the lever. If it's further away, it requires a greater turning force. Now you might say, is that not offset by the shorter pieces? It doesn't. As I said, irregular. They could be reasonably close, but the general gist is the longer it's distributed, the harder it is to turn. Okay? So body's turning, if it's really close to the center, it's easy to rotate, but if it's a bigger one, it's harder to rotate. So if I was to, we'll just go on a really basic level here. If I had this here, followed by this one here, and they're both just squares, which one's harder to rotate? The big one. The one that has a lot of its mass further away from the center of rotation. Okay? That's all you really need to take from that at the moment. Now, if a mass is a measure of a body's difficultness to move, moment of inertia is a measure of a body's difficultness to rotate. How hard is it to rotate a body about a certain axis? Okay? So that's basically the gist of what is moment of inertia. Okay? So what I'll do next is okay, we stop here for a minute. The moment of inertia of a uniform rod of mass m and length 2l about an axis through its midpoint, perpendicular to its length, is 1/3 ml squared. That's what I have to go about proving. Okay. So what I'm going to do is I'm going to first make my rod. My rod will be, we'll just do this here. Okay. Now, in the center of the rod, I have its axis that it turns on. The center of gravity, so to speak, of the rod. All the weight would act through the center, and if I was turning it around, it would rotate around this way into the board. Basically like that, yeah? Okay? Now, once you have that done, once you know that it rotates that way, what you're going to do next is you have to always find what's called mass per unit length. It's going to be mass per unit length because this is technically one-dimensional. The rod is considered one-dimensional. Okay. So you find out what rho is. It's always step number one. Find out what rho is. Rho equals mass divided by length. Okay. The length of the rod is 2L. That's L to the left, L to the right. Please make a note right now that all our formula in our log tables are based on a distance of 2L. Okay? So if we had a distance of 4L, we'd have to scale up our formula by the L value by 2. Okay? So it's mass over length. It's of mass m. So you put m and you divide it by 2L. Okay? Next thing you do, isolate m. Mass therefore equals 2 rho L. Can anybody tell me the units of the unit of rho? Kilograms per meter. Yeah? How much mass is in a single length? Okay. Next thing, after you finish that part, what we're going to do next is we're going to find out what delta m is. We're going to represent a single little piece of mass. We call it delta m. Okay, that's some random piece of mass. How many of them is there? Pretty much infinite number, isn't there? Depending on how tiny, how small you chop them up, how small you chop up your rod. Okay, so delta m, and it's going to be over a little distance delta x. Okay, so do you understand that delta m, if I was to zoom in on it, like with a microscope, delta m is still in the shape of a rod. Its mass is delta m, and its length is delta x when I zoom in on it. Okay, so the mass delta m equals your mass per unit length, your rho value, multiplied by the length of the piece of rod that you're actually talking about. Okay, stop there. Okay. So the next part after that is we basically have to figure out what its inertia value is. The whole point of the question is, can we figure out that the inertia of this rod is 1/3 ml squared? What's the inertia formula? I is equal to the sum of every delta m r squared. Okay, that's what we have to figure out. Step 1, replace your delta m with rho delta x. Okay, so we're going to have E equals rho delta x r squared. Okay, next step after that is what is your r value? Okay, now by definition, this delta x value here, we're going to say that it's a distance x from the center of gravity. Is that alright? So any delta x's we use are always going to be a distance x from the center of gravity as part of our proof. Because remember we said that the inertia depends on how far you're away from the center of gravity? The inertia of any piece of material depends on how far you're away from the axis of rotation. So we're going to define that as x. So that's now going to turn into equals some rho, what's it? That'd be rho x squared delta x. Is everybody happy enough with that? Now, we got to integrate next, okay? Now, how do you integrate this? Well, to integrate this, you always look around the center of gravity. Okay, so we're going to look around the center of gravity. Now, if this is the center, how far can you go to the left? The lower limit is minus L. L to the left. What's the upper limit? L to the right. Plus L to the right, okay? So when I go back down here, it's going to be L to the right is the upper limit, minus L is the lower limit. We have rho x squared. Now, what does delta x change to when you then put it into integration? Dx. Okay. Now, once you've done this part here, and this is still inertia, you integrate your rho x squared. Okay, and what is the integral of rho x squared, anybody? Just integrate the x squared. You get x cubed over 3, and you get the rho on the front, and you have L to minus L. Okay, now what we're going to do next is we're going to integrate that, and I'll do it up here. Okay, so what I'm going to get is rho L cubed over 3 minus rho bracket L cubed all over 3 as well. And just put that in square brackets. That turns out to be minus rho L cubed over 3, and a minus by a minus makes a plus. So it's going to be rho L cubed over 3 plus rho L cubed over 3, and that gives me 2 rho L cubed over 3. The whole point was 1/3 ml squared, right? 1/3 ml squared. I need an m. What doesn't belong in this formula? What letter definitely doesn't belong in this formula? Rho. Sewn in on your rho. Rho equals m over 2l. So 2 times rho, 2l cubed over 3 times rho, but we're going to get rid of rho. And rho was m over 2l. The 2's cancel. L cubed divided by L. L squared. 1/3 ml squared is your inertia. Okay, and that's first proof. In the proof I just did to begin, what we did was we had a rod, and the rod was rotating about its center, like so. We found this to be 1/3 ml squared. Everybody happy enough with that? Okay. Now all of a sudden we have a rod, same rod, still of length 2L, but this time it's held through an endpoint. And what does that mean regarding its axis of rotation? When it's held through the endpoint, what way is it going to rotate now? Like that, yeah? Because it's rotating about its endpoint as opposed to its midpoint. Okay? Like last time, it's 2L in length. Center of gravity would still be here, but the axis of rotation is no longer there. Okay? So, what we're saying is it's 2L going in this direction here. What did we set up first last time? We set up our rho value, a definition of rho value, yeah? Our rho value is mass per unit length, or mass, total mass over total length. Our rho value is m over 2L, which in turn leads our mass to be 2 rho L. Everybody on board so far? Now, what we then do is we pick a random piece, a random chunk of rod. And what did we say about that random chunk of rod? We define it, its mass is delta m, and we define its distance away from the axis of rotation as x. We then take a zoned in look at delta m. Delta m is also in the shape of a rod, and therefore it has a length. We'll call that tiny little minuscule length delta x. Is that alright? Now, once we set up that system, we're then open to setting up our equation. Okay, so we can write down that delta m, the mass of this tiny little rod, equals the mass per unit length multiplied by the length of this rod. Is that right? Mass per unit length multiplied by the actual length. Yeah, I'll just do this in turn. That's the mass per unit length. This one here is the actual length of the rod. Okay, now that you've done that, what you're going to do next is you're going to write down your definition of inertia. Inertia equals the sum of delta m r squared. Okay, so delta m r squared. Now, our inertia therefore equals the sum of, change delta m into rho delta x, change the r squared value to what? R is defined as the distance of your mass away from the axis of rotation. So what's that going to change into? X. Okay, so it's going to be rho x squared delta x. Integration wise, can anybody make a prediction on what you think the limits might be? Now remember, the limits is taken from the axis of rotation. What's the lower and what's the upper? Perfect. Right, 2L is the upper, and the lower? 0. Really good. Okay, and then we change what this here into? Huh? Dx. Now all of a sudden, what we have here is I equals rho x cubed over 3, 2L over 0. Yeah, and then integrate it, and it's going to be I equals rho 2L cubed over 3, 8 rho L cubed over 3. Like last time, the rho doesn't belong. Okay, so we say that rho equals m over 2L. So we say 8L cubed over 3 times m over 2L. And then convert that answer into 8 divided by 2 is 4. 4ml cubed over 3. Was that the prediction you think? That it was harder to rotate it about its end than about its center? Because the majority, a good bit, this part here of the rod is much further away than if you rotate it from its center. Okay, so it was always going to be a bigger inertial. It was always going to have a bigger inertia because it's always going to be harder to turn. So guys, one other thing, just this L here cancels with that L there, so it's actually ml 4 ml squared over 3. Well done. Okay.